A multi-class model can look calibrated overall, while one class stays dangerously overconfident. Classwise reliability diagrams and OneVsRest calibration expose and fix that blind spot with scikit-learn. After this, you'll understand how to assemble a pipeline that plots per-class calibration gaps and repairs each class separately. I'm Professor Pi, teaching AI foundations with simple Python. Calibration matters when probabilities actually drive decisions. Picture an intent classifier that reports 90% confidence for a label that in reality fires far less often. Teams route work based on that number, and users see the wrong outcome. A single aggregate metric will happily hide that skew. So, we need per-class checks that point to the offending label. This lives in evaluation and post-processing, and it's compact enough to run on typical prototyping sizes. Fixing a miscalibrated class can cut costly misrouting by making probabilities match reality. The core plan is straightforward. We'll create a small deterministic 3-class dataset, train a baseline model, measure class-wise probability errors, draw reliability curves per label, and then repair the worst classes with OneVsRest calibration. The payoff is clarity and targeted repair. The trade-off is extra compute because we fit per-class calibrators. But that overhead is often worth the improved downstream behavior. We will build a small but deterministic 3-class example so you can see numerical diagnostics and plots that match every time. The code stays focused on the concept, not heavy engineering, so the calibration moves are obvious before you scale them up. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let us first make the dataset and keep the split stable so later comparisons are meaningful. This snippet builds a deterministic 3-class dataset with scikit-learn. Calibration is easiest to reason about when the data split is stable. So make classification creates X and Y once, and train test split preserves class balance with stratify equals Y. The features are synthetic, but the setup behaves like a normal multi-class project. Train on X-train and Y-train. Then hold X-test and Y-test back for honest probability checks. The random state values keep the screen output and later model comparisons repeatable. The visible output confirms the train and test sizes before any calibration work begins. A held-out set is ready. So next we fit a baseline model to get raw predicted probabilities and an overall loss number for context. This example fits a baseline RandomForest classifier with scikit-learn and measures its overall probability loss. A multi-class model can look acceptable when you only inspect one aggregate number, because log loss blends mistakes across every class and every row. The important object here is raw prob, the full probability table returned by predictproba for X-test. N-estimators controls how many trees vote inside the forest. Increasing it often makes predictions less noisy, while decreasing it makes the demo faster but can make the probabilities jumpier. The output gives the overall log loss and the class order used in every probability column. An aggregate loss hinted at a problem, but it does not tell us which label is miscalibrated. So we compute OneVsRest diagnostics to find the worst class. This code turns the multi-class test labels into OneVsRest targets and scores each class separately. The aggregate log loss from the previous step can hide an overconfident class, so Label Binarizer creates Y-test with one binary column per class. Then, Brier score loss compares each class probability column in raw prob against the matching yes or no target column. Raw Brier is a compact diagnostic table, and worst I keeps the column index aligned with the class label stored in worst. The visible output names the class with the largest Classwise Brier score, which tells us where to focus the calibration repair. With the worst class identified, we want a visual diagnostic so humans and stakeholders can see where probabilities diverge from reality, one class at a time. This snippet plots one reliability curve per class using scikit-learn calibration curve and matplotlib. Each pass through the loop treats one class as positive and all other classes as negative, which is the class-wise view we need. Calibration curve returns mean predicted probability and observed positive fraction for the bins, and plt.plot draws those points against the diagonal reference line. N bins changes the smoothness of the picture. More bins show finer structure, but need more data per class, while fewer bins are steadier but less detailed. The output confirms that all class-wise curves were prepared for the diagnostic view. After you see a skewed curve for the bad class, the next step is to repair probabilities for each label independently, rather than forcing a single multi-class mapping to be perfect everywhere. This example applies class-wise calibration by wrapping scikit-learn CalibratedClassifierCV inside OneVsRestClassifier. Instead of asking one multi-class probability table to be good everywhere, OneVsRestClassifier trains a separate binary problem for each class. CalibratedClassifierCV then learns a sigmoid mapping for each of those OneVsRest scores using cross-validation, so CalProb gives repaired probabilities in the same class order. The CV equals 3 setting reserves different folds for calibration. Increasing it uses more folds but costs more model fits, while decreasing it is cheaper with a less stable calibration estimate. The output compares the previously worst class before and after calibration. This toy shows the pattern you can apply to intent classification or risk models. Swap in your real X and Y, keep the class-wise binning, and wrap the classifier in OneVsRest plus CalibratedClassifierCV, so you can target the specific label that misleads users. You walk away with 3 practical things: a per-class diagnostic that points to the misleading label, a straightforward per-class repair strategy, and one caveat: you need enough examples per class for reliable calibration curves and bins. If you want to explore further, rerun the class-wise calibration with CV set to 5 and try isotonic calibration for the worst class to see if the curve shape improves. That trades more compute for potentially better fidelity when a label needs a non-linear mapping. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.